Hello, geometry class. Alright, so what we have here is a quick little demonstration I want to show you about triangles. So when you're doing lesson 1.5, you're going to notice that you're going to need to figure out what are the differences between all the different kinds of triangles that you'll be studying. We have a right triangle, we have an acute triangle, obtuse triangle, scalene triangle, equilateral triangle, and then an isosceles triangle. So what I'm going to do is I'm going to click on these vertices for each of these triangles, and I'm going to move them around like this, for example. And I want you to notice how is each triangle moving around differently, and see if you can figure out what kind of a triangle is each one here. Okay, so here you can see there I'm moving each of the each of the vertices in this particular triangle. Okay, and what's happening with the angles, with the sides, as I push in, push out, as I move up and down. Okay, now let's compare it to, for example, this one. I'm going to take this vertex G and I'll move it around. What's happening with the sides and the angles in this triangle? If you'll notice, their sides are staying equal. The measurement of the angles, if you notice, are actually staying equal. It doesn't matter whether I spin it, pull it out, push it in. And the same would happen if I take any of these other vertices. Well, this one just moves the triangle around. Like, for instance, I can stretch it out and then come over here and just move it around. If I take this vertex, same idea, it does the same thing as vertex G does. Okay, so that triangle, as I'm sure you've guessed, is an equilateral triangle because all of the sides remain the same length, and all of the angles in here remain the same measurement, no matter how you move it around. It can be a small equilateral, it can be a big equilateral. Like here's a small one, right? If I push it in, a real tiny one, but it's still equilateral because all three sides are the exact same length and all three angles are the exact same measurement. Or it can be a really big one, same idea. So let's take this one. What happens if I move vertex M of this particular triangle? I'm pushing in and I'm pulling out. I'm pushing up and down. That's vertex M. But vertex N, what happens here? If you'll notice what's happening with angle M as I move N around, it doesn't seem to matter what I do to N, the measurement of the angle M remains the same. Let's see what happens when I move vertex L. Okay, that just moves the entire triangle. Okay, so I'm going to do this move one more time. You might tell by now that this is a right triangle, and the reason why is because angle M happens to always be 90 degrees. You see, this side is what you can say is straight up and down, if you want to think of it that way, and this side is straight across. But the distance between the two sides, which is the angle in between, is 90 degrees, and it always remains, and that's what you call a right angle. And when a triangle always has a right angle, you have a right triangle. Okay, so this purple triangle you can see is an equilateral triangle. This green triangle you can see is a right triangle, but these are the harder ones. So what's going on here? I want you to take notice what's happening to the measurements of the angles. Are they obtuse or are they acute? And I know all of you remember that an acute angle is one that it measures to be less than 90 degrees, and an obtuse angle is one that measures to be more than 90 degrees. So if you look at angle B, for example, right now, that's definitely an obtuse angle. But if you look at angle A and then angle C, they're both acute. Definitely much narrower than 90 degrees. Over here, let's take note what's acute and what's obtuse, and how are these vertices moving differently in this triangle. Do you notice that the length of sides F and D, as well as the lengths of sides F and E, are, well, no, I didn't do that right, are now, they're moving, right? But the length of side D and E is staying the same as I move, whoops, what am I doing? As I move vertex F around. Okay, does that happen over here? When I move vertex A, looks like B and C is staying, but sides AB and AC are moving. What happens if I do this? AB is staying the same, sides BC and BA. Or BC and AC is moving. How about this? Okay, same idea, but what's happening to the angles and the measurement of the sides? So I'm not going to tell you what these kinds of triangles are, but I will say that an acute triangle is a triangle that has 3 acute angles. So if all 3 angles in the triangle, 1, 2, 3, are less than 90 degrees, then we have an acute triangle. An obtuse triangle is one that has 1 obtuse angle. So I have 1 angle that happens to be more than 90 degrees. Let's say if you look at angle B, then and your other 2 can be acute, then you have an obtuse triangle. Okay? So let's think about, I want you to think about, you can play back this video as many times as you need to, but think about what's happening to these 2 different triangles. How are they different? How are they the same in terms of what happens to them when I move the vertices around? The other thing to notice is a scaling triangle. A scaling triangle is a triangle with no congruent sides. So if I were to move, let's say, this in and maybe over like that, let's say like this, I have 3 different lengths of sides. One's really short, this one's definitely the longest one, and side AC is definitely the middle size one. So that's a scaling triangle. So when you play the video back and you look at what happens to this red and blue triangle as I move them around, you can think about when do they become a scaling triangle, and when do they become an acute triangle, and when do they become an obtuse triangle. And the only other type of triangle to know about is an isosceles, and that's where you have at least 2 congruent sides.